Alright, so welcome to the day 2 video on the beginning of universe notes. Today's topic is going to be looking at spectroscopy. It's a big fancy word for the study of light. And our essential questions today are: what is spectroscopy? How can we use spectroscopy to get information from distant objects? So yesterday we talked about how the way in which we learn about objects that are far away from us is much different than the way in which we learn about objects that are close to us that we can observe with our senses. So today we're going to talk more about how is it that we actually get information from a distant object. Even though we can't observe it with our senses, it is telling us information from the light that it is sending us, and so spectroscopy is the study of basically taking that light and turning it into information. What is that object telling us about itself? So we're going to go ahead and get started. Again, I tried to underline things that you need to write down. And again, feel free to pause the video if I'm going too quickly. I'm going to try to go through things fairly quickly here, but feel free to pause the video and allow students to write if they need to. So we're going to start out looking at what we ended yesterday with, which was looking at the visible spectrum, or what we call the electromagnetic spectrum. And so yesterday we talked about the major difference between the different types of waves is the wavelength. And so when we look at this particular spectrum, this is what we call a continuous spectrum. This is the electromagnetic spectrum. And you can see the Roy G. Biv letters underneath it to denote the different colors of the rainbow. And so the red end of the spectrum is where we have the long wavelengths, and the blue end of the spectrum would be where there are shorter wavelengths. And so remember, this is just a piece of the entire electromagnetic spectrum, and this is just what we call the visible spectrum. These are the colors that we can see with our eyes. Anything outside of this part of the spectrum is going to be unable for humans to be able to perceive. So this picture here is just kind of a way to organize the different types of waves in the electromagnetic spectrum and kind of how they compare to each other. So if you look up here towards the end where the radio waves are at, those are the longer wavelengths. You can see the distance between the peaks of the waves is much larger than if you go over here down to the gamma ray end of the spectrum. You can see that the distance between the peaks of the waves is very much shorter. So these would be your short wavelengths down here. These would be your long wavelengths up here. And in comparison to this, a radio wave, its wavelength, if you were to compare that to, say, take an analogy of the distance there being equivalent to Mount Everest, the height of Mount Everest, all the way down to a gamma ray, which would be the distance of an atomic nucleus. So we're talking about a very, very large difference between the distance of a radio wave and the distance of a gamma ray. These powers of 10 also do a pretty good job of showing you the difference between that. Remember, a power of 10 would be adding a 0 each time or taking away a 0 each time. So you can see that we're going from 10 to the 4th power all the way down to 10 to the negative 16th or 18th power. So this just does a good job of showing you the difference between long wavelengths over here and short wavelengths over here and the actual distance between them. And you can notice that the visible spectrum is a pretty tiny part of the spectrum, actually, and so with our human eyes, we're not actually seeing a lot of the waves that are going on around us. So now we're going to take a look at spectroscopy. And spectroscopy, like I said, is basically a fancy word for studying radiation or studying light and using what's called a spectroscope. So a spectroscope uses a prism or what's called a diffraction grating to separate radiation into its different wavelengths. So when we see white light, we're actually seeing all of the colors mixed together. Oftentimes we tend to think that all the colors mixed together would give us black, but in terms of light, when we see white light, really what we're seeing is all of the colors of the visible spectrum combined. So what this spectroscope does, or what a diffraction grating or a prism does, is it takes white light and it separates it into the different colors of light. Because all those colors are in there, they're just all mixed together, and so to us it looks white. but when we separate it out, we can see all the colors of the rainbow. And so that's why you see the different colors of the rainbow in an actual rainbow after it's rained, because the water in the air is actually acting like a prism, and so the light is shining through that water, and the water is diffracting the light into the different wavelengths, so we see the different colors. So spectroscopy is just simply the study of kind of breaking down light into different wavelengths and studying each one of them separately. So this is what I'm talking about in terms of how a prism works. So you can see the light source over here in the bottom left-hand corner. This is a white light source. That white light is being shined through what's called a diffraction grating here, through this little opening, and then into a prism. And the prism then is what kind of separates that light into the different colors. So you can see all the different colors of the rainbow over here. These colors are all in the light that's coming from this light bulb. So when they're combined all together, we see white. When we separate them out is when we see the different colors. So that's kind of a backwards thing. We tend to think of all the colors being combined would be black, but really white light actually does contain all the colors of the spectrum. So using spectroscopy on radiation from space. So we talked yesterday and today so far about how we can learn about distant objects from the light that they are emitting, or the radiation that they're emitting towards us. So these are some things that we can learn about a distant object, something like a star or a distant moon or planet or galaxy, based on the light that it's emitting towards us. And so we study it by using spectroscopy, and we can determine things like the temperature of that distant object, the composition of it, what is it made up of, and the motion of it, in terms of, is that object moving away from us or is it moving towards us. So these are three things that we can learn about a distant object, whether it be a star, planet, galaxy, whatever it might be. We can learn all of these things simply by studying the light that it is emitting towards us. So the word spectrum, first of all, the word spectrum is a plural word. Spectra is the singular for that. So there are different types of spectra that we can observe, and what you would see if you were using a spectroscope might look something like what you're seeing on the screen here. And so I'd like you to draw these in your notes. For the continuous one, you can probably just kind of shade it in with your pencil. The emission, you'll want to just kind of shade in most of it and then leave openings where the bright lines are. And then for the absorption one, you'll kind of want to leave it mostly open and only shade in the spots that are dark on here, so that you're kind of doing the opposite of an emission spectrum. Okay, so go ahead and draw those as I'm talking here, but a continuous spectrum is going to show us all of the colors of the rainbow with no interceptions. There's no parts of it that are missing. That's why it's called continuous. An emission spectrum looks like this, where you have not very much of the light coming through at all, but just a few bright stripes that are coming through. And then absorption spectrum is more like the continuous, but there are sections of it that are taken out. And we're going to talk about why those sections are taken out in just a minute here. So go ahead and draw those in your notes. If you need to pause this, you can do that, but I'm going to go on. Alright, so the types of spectra we just talked about, there's three different types. There's continuous, there's emission, and there's absorption. So a continuous spectrum is typically the spectrum of light that we would see from a hot, dense object like a star or a light bulb. So that would be the one on the top down here, the high density hot matter producing light, and that's where we're going to see the continuous spectrum. We're going to see all of the colors of the visible spectrum coming in the form of white light. The second kind is what we call an emission spectrum. This is typically produced by a hot gas, something that's not very dense. This would be something like a star's atmosphere, or what we call a nebula, which is similar to a galaxy. And so we're going to see an emission spectrum where a lot of the color is not there, but rather only parts of it are seen. And this is because different gases are going to burn at different temperatures, and they're going to produce different spectrums of light. And so each gas is going to kind of give us a different pattern here of which parts of the spectrum it emits. And then this last one here, if it got kind of cut off for you, I think at the bottom here, but this would be what we call an absorption spectrum, where we have light being emitted from something like a light bulb or a hot, dense object like a star. But then it's passing through a gas that is taking out parts of the spectrum. So the reason that these black lines are here is because this cold gas that the light is passing through has actually removed these parts of the spectrum. So this gas here has removed these parts, and so what you're seeing is the continuous spectrum with parts of it missing because it's passed through this cloud of cold gas. Okay? So make sure you get all these definitions down in your notes before you move on to the next slide. So in emission spectra, we're going to talk about each one in a little bit more detail here. And again, I'm gonna go pretty fast through these, but again, if you need to pause and stop and so that you have time to write down, please do that so that you get all the information down correctly. So the emission spectrum is when burned, every element produces a spectrum with a unique set of bright lines. So for instance, this one down here is hydrogen, and it produces these lines. This is mercury, that produces these lines. This is neon, which produces these lines. So each element on the periodic table is going to, when it's burned, it's going to produce a different type of spectra. And so this is helpful for scientists when they're trying to learn something about what the composition of something is made up of. Is it made up of hydrogen, or is it made up of oxygen, or something like that? These spectral lines are going to tell them which elements it's made up of, because each of them has their own. So it's kind of like a fingerprint. If you were trying to figure out whose hands were on something, you would take a fingerprint off of that to do that. Well, these lines act like fingerprints. So when we see spectral lines that look like this, we know it's hydrogen. Or when we see it looks like this, we know it's mercury. So this is how we can kind of learn some things about the composition of a star or a distant object. So this is a little bit of practice for you. So these are all what we call known spectra. So these are different elements, and these are the spectrums they produce. Down here you have an unknown spectrum. And so this is an example of how scientists can determine whether which element is producing the spectra. So this is the unknown one. So what you would want to do is try to match it up with the one that matches most closely up here. So if we do that, we can see that this one down here, the unknown, very closely resembles this one, which is Sr, or what we call strontium. So that's an element on the periodic table. So this one down here would be strontium, or Sr. Then you have an absorption spectra. This is where the clouds of cool gas are taking out parts of it. So the black lines that you see in the continuous spectrum are taken out by the cool gas that it has passed through. And so this is another example of how we can determine what that cloud of gas is made up of, is to look at which things it took out of the spectrum. So if we do an example here, if we want to find out what's in that cloud of gas that it passed through, we can look at hydrogen, looks like this, mercury, neon. This is the unknown spectrum here. We know that it's passed through a cloud of gas, but we don't know which one what was in that cloud of gas. So we can determine that if we match this up with the most close matching spectra. We would say that that gas is, or that cloud of gas is made of hydrogen, because it matches this one most closely. All right, and then we've got a little video clip here that we may or may not get to finish here before my video cuts off, so we'll watch about a minute of it here. Whoops, that didn't work. Let's try going back.
Our only contact with the distant stars is their light that's journeyed across the universe to reach us, and encoded in that light is the key to understanding what the universe is made of. And it's all down to a particular property of the chemical elements. You see, when you heat the elements, when you burn them, then they give off light, and each element gives off its own unique set of colours. So this is strontium, and it burns with a beautiful red colour. Sodium is yellow. Potassium is lilac.